like that, if it is asymmetrical, so the Lorentz force, that will be a differential Lorentz force will be applied, and depending on the Q factor of the resonator, if you can increase the Q factor to a high value, and by pumping this with a microwave source, it is possible to generate a net force. So in this case, our satellite mass will come down and the cost of the launch will go down, especially for interplanetary mission. This will come to very useful. Next, please. Now a little bit I would like to highlight that is our activities in the Indian space program. Is for communication, navigation, and the Earth observation, and also the outer space exploration. So just a glimpses of the activities. I will just go to the next few slides. Next, please. So that is the communication. It is our Indian national satellite, and for navigation is the Indian regional navigational satellite system, and for the remote sensing it is Indian remote sensing satellites. And apart from this, we have the launch vehicles for this PSLV and the GSLV. Now these are the, just a minute, yeah. These are the different series of the INSAT satellites. And previously, all the INSAT satellites, it was that launches were imported launch. We did not have the technology to launch it. But now with the GSAT-14, that is our indigenous, that is Mark II, that has been developed. And last year in the January 2014, that the success we got to launch indigenously, that is GSAT-14 using our GSLV Mark II. And now a lot of satellites have been planned, and there are international collaboration also seeing our success. Like I have a presentation in the afternoon, so there I will show what are the international collaboration with us based on our success. Especially with the JPL, JAXA, we are planning few of the missions along with those organizations. Okay, next please. So these are the application of the communication satellite. As I said, the applications are there in the communication, that in the broadcast, meteorology. So these are the different one we are using. It is a day-to-day life. Next please. This is the application of the talkback program, and that is the teaching, and this being used in the universities. That is, you can using the satellite distance education, the teaching aid, it is possible through satellites. That is our Q-band transponders are being used for this distance education. Next, please. So this is an important, again, the application of the communication satellite, that telemedicine via satellite. So those medical centers at the villages, through satellites, they can communicate with a panel of doctors, specialist doctors at the health specialist center. So this has been possible with our Q-band transponder of geostationary INSAT and GSAT satellites. Now this is the Earth observation satellite. So we have this program of two types of Earth observation. There is the microwave Earth observation and the optical Earth observation, where different types of cameras are used. So microwave, so far as since I am working on the microwave regime, so here again we develop two types of sensors. That is the passive sensors. So radiometer. It started with the OceanSat, that is the MSMR, multi-frequency scanning microwave radiometer, followed by the scatterometer, RISAT, and there are many microwave remote sensing there on the pipeline in the coming few years. Yeah, so these are the different applications of that is the Earth observation satellites. Next, please. Now, this is the interplanetary mission, as I said, this is the Chandrayaan-1. So here, the challenge is that is the Earth's orbit to transfer it to Moon orbit. So this was launched in 2009, and it was a great success. And this success motivated to go for a next mission that is called the Mars Orbiter Mission, MOM. And that success we got in 2014 24th of September, when our, that is the payload, and that is the satellite, it was able to inject into the Mars orbit. Next please. Yeah. So these are the payloads it was used in the Mars orbiter mission. Next please. Now, what are the trends in the microwave technology? So far as the satellite technology is concerned, that is, we need it should be faster, cheaper, and the smaller. So always the necessity is there. That is, you get a smaller device, and it should be having a broader bandwidth. It should be higher efficient. So these are the devices. That is the silicon carbide, then gallium nitride. These are the devices that are being developed, and these will replace these MOSFETs and amplifier modules. And also there is a lot of development, or there is the trend is the microwave test equipments. Like these instruments which we used to use some few years back, now it is very sophisticated, very automated instrumentations are possible, and very accurate measurement system. And you can get the network analyzer up to 500 gigahertz frequency band. So these are the new developments. Of course, we are to depend for all those things to the customers, that is our vendors like Aziland, Rodeswords, and all these people. But still, what I said, that globally, that microwave measurement system has got a lot of innovations and lot of new things. Microwave propulsion, that is also a new field already I discussed. Next please. Now these are the other like visible light. You can go to the next. This. So fiber optic data transmission system. So here also it's a very important, because here you get a that is the disadvantage of that microwave, that radiation exposure is not here. You get a very high bandwidth. But frankly speaking, this is a challenge for us, the satellite. Our bread and butter is satellite communication, and there the microwave is used. But hope this two fields will go in parallel. That is, the time it will never come a situation when you don't have microwave communication. You cannot depend totally on optical communication. So this thing will go in parallel. When you get a very high data rate, high speed, definitely these things will be used. But when you use a global communication, definitely the satellite communication cannot be beat by fiber optic communication. Next please. Yeah, you can skip this slide. So these are the another, there is the infrared thing. There is the application of the infrared, that is the band of microwave spectrum. So there, again, this is like a infrared radiometer. That is, anybody, it radiates the radiation. Now, depending on the composition of the body, the temperature profile will be different. So a thermal imaging can be done using infrared. And in our INSET 3D, that infrared sounder to study the profile of the atmosphere, different layer of the atmosphere. There is especially the oxygen. But disadvantage is that infrared thing, it cannot be used when there is the cloud and all these things are there. So again, there the application is the microwave only. Okay, next please. Then that is the ultraviolet waves. This is they have the shorter wavelengths as compared to the visible light, and there the uses of these are the sterilizing material, then water disinfection, and the that is the security images. Next please. The X-rays. So X-rays, it is very widely used in the medical sciences for medical imaging, then airport security, inspection, and industrial wells. Next please. Gamma rays. So gamma rays, again, this is the smallest wavelength in the what we are using. That is used for the food irradiation, then cancer treatment, and the sterilization of surgical instruments. So with this is the end of my presentation. And if you have any question, you can please ask me.
Thank you, sir.
Thank you.
Speaker, Dr. S.P. Chakrabarti.
Gupta, Honorable Vice Chancellor, AIS University, Dr. Soumyabira Chakrabarti, Keynote Speaker, Professor K.S. Sharma, Conference Convener, Dr. Rakhi Gupta, Registrar of the AIS University, Professor Pradeep Bhatnagar, Dean, Faculty of Sciences, dignitaries, resource persons, delegates, and guests in the audience. It is my proud privilege to propose a formal vote of thanks on behalf of the AIS University at the inaugural ceremony of the two-day national conference on recent trends in microwave techniques and optical communication. On behalf of the AIS University, I take this opportunity to express my deep gratitude to Professor Chakrabarti for so very kindly acceding to our request to deliver the keynote address. Thank you, sir, for your presence and insights. Your address, sir, has set the tone for the deliberations that are to take place over the next 2 days. The conference has been organized to create a discussion forum for researchers, academia, people in industry, and students who are interested in the latest development in the field of microwave techniques and optical communication. I am thankful to all the invited speakers for taking time out of their busy schedule to be here to speak on this very contemporary topic. Thanks are also due to all academicians, industry experts, delegates, and students who have come from far and wide to attend the conference. I sincerely hope that your inputs and interaction during the course of this conference will make new contributions to the field and will be of immense value in times to come. My thanks are due to Dr. Ashok Gupta, Honorable Vice Chancellor, the AIS University and Conference Chairperson for his continuous support and invaluable guidance throughout, which has given this 2-day event its present shape. Also, I would like to sincerely thank Dr. Rakhi Gupta, Registrar of the AIS University, for her guidance and ready solutions for the smooth conduction of the program. I am also grateful to Professor K.S. Sharma for helping us to organize an event of such a stature and magnitude, and Professor Bhatnagar for all the help and guidance extended to us by him. The event would not have been possible without the team spirit of all my colleagues from the Department of Physical and Computing Sciences, student volunteers, research scholars, and the technical and support staff. Lastly, I thank all the media persons whose ample coverage of the conference will bring this contemporary issue closer to public interest and notice. With the hope that this conference will accomplish all its objectives, I wish it all the best. Thank you once again.
With the first technical session at 12 noon sharp. And I also request all the oral presenters to...
Sharma and Dr. Ritu Jain. At the very outset, I would like to express my heartfelt thanks to you and everybody on the organizing committee to giving me an opportunity to be here this morning and to share some of the very recent concepts in the area of microwave physics. There are 3 speakers in this session, and there is 35 minutes for each presentation. The first speaker is Dr. Kummukanne. He is presently is a professor in the School of Physical Sciences, ASRPEM University, London, and he has about 20 years of teaching experience and in the area of electronics, microwave and microprocessor and microcontroller, over 70 publications in international journals, and has guided Professor Kummukanne. He has guided about 14 PhD students and 10 projects he has already completed, and awarded a fellowship by Northeastern University, Boston, to carry out PhD postdoctoral work in USA. The visiting scientist at the Munster University, Germany, and awarded the Young Scientist Award, Indian Science Congress Association, Calcutta, in the year 1995. Worked at the Tokyo University, Japan, as a scientific professor Yagahara. So this is my great privilege to invite Professor Kumbakarna to deliver his talk.
Me here or participant of this program.
Pointer there.
So I will give a talk on time domain reflectometric technique from 10 megahertz to 30 gigahertz. And second point I will discuss on the dielectric spectroscopy. And third I would like to discuss on hydrogen bonding. I am Dr. Kumar Khane, at School of Physical Sciences, SRT. Next. This is next. This is on back. This is School of Physical Sciences, SRT University Nandar in Maharashtra, and it is established in 1995. The School of Physical Sciences, we are running the 4 courses: astrophysics, electronics, microwave, fiber optics, and material sciences. Professor Chakravarti already explained you electromagnetic spectrum just now in keynote address. You will find that this is a radio wave up to gamma ray, and your microwave is here. After radio wave, there is microwave, and the wavelength also here. See, the radio wave is longer wavelength, here is shorter wavelength. So microwave is a range near about in micron. That's why it is microwave. And that's why there are a lot of application we find. Just now, Professor keynote address, he explained all this application. And the frequency range also, we will see that this is a lower frequency and this is higher frequency. You will get a lot of information from this electromagnetic spectrum. And as you see that electromagnetic spectrum can be detected by different techniques. Particularly in the optical frequency, women can detect only the 7,000 to 4,000. Means microwave are not, we cannot say invisible, it is an invisible region. That's why it is very important to see and study in this region. Next. So what is microwave? We are just focusing on particular microwave. Microwave has different band, L band, C band, J band, B band, and different application you find that. So every band requires different sources, different transmission line, and different what is called detection, and we just classify it. Is a dielectric spectroscopy. Whenever you want to study the microwave dielectric property, the frequency response is very, very important. So what dielectric spectroscopy measures the dielectric properties of the medium as a function of frequency. First, see first graph, you will find the epsilon prime, which is frequency dependent. Depending upon the frequency of source and how many expertise you have, you can study and you can measure the dielectric constant with frequency dependent. And second factor we will get from the dielectric spectroscopy, dielectric loss, which is also frequency dependent. Whatever the frequency available, you can see the frequency is epsilon double prime with loss factor, right? And third point, we can determine the dielectric relaxation with basic property. It's a very important peculiar property, dielectric relaxation. So on that basis, once we analyze the relaxation time, relaxation analysis, we will get the different information, molecular information, and how the molecules or whatever the entities relax, and then what frequency that information will get, and it's a time dependent. So depending upon the time taken by these molecules, so we'll get the different relaxation. So that's why this graph in dielectric spectroscopy, particularly people are interested to get the information from lower frequency to higher frequency, and what time relaxation, whether it is picosecond or nanosecond, depending upon the availability of the instrument. So in dielectric spectroscopy, polarization phenomenon is important. With what frequency you are working. So this is a dielectric property, and depending upon the what frequency you are using. Whether you are using the microwaves, you will get the orientation polarization. If you are working on atomic polarization, so you will get the different thing. Electronic polarization, depending upon the frequency applied and the instrument available, you can study the different polarization. So dielectric spectroscopy, in terms of, we say that it is broadband dielectric spectroscopy. from lower frequency 1 Hz to up to 1 terahertz. So depending upon your what is instrument available, you can study this. This is lower frequency. In cost point of view, you see this is a lower cost. If you go higher frequency, the cost is very, very expensive. So people are using in the university levels DC, TC, alpha, TDR, impedance analyzer to determine the dielectric parameter. And so we see that this is the graph. This is the technique normally used in the time domain. The time domain technique start from this 10 to 10 Hz, and lower frequency LCR meter people are using. High frequency again impedance analyzer, total analyzer people are using. And what time? Relaxation time will get the information about 10 to minus 12 and less than. So relaxation time is time what material you are studying depending upon. So this is the what you call information about the what. Suppose you are interested in the finding out the bound water or biological sample, so you have to go in this band only. But our TDR is using information about the 10 to 6 to 10 to 10. Still people are working on the THZ. We are also interested to go in THZ frequency. And most of the university people are running a LCR meter, material science analyzer, and you will get the different phenomena in the particular frequency range. So on that basis we can classify dielectric spectroscopy in frequency domain as well as time domain. What is the frequency domain? It's the fixed frequency. Once you have a fixed frequency, you can study the dielectric constant from epsilon prime and dou prime. If you have a variable frequency, you can study the dielectric constant in variable frequency. In time domain, there are again two types. One is transmission method and reflection. So my talk is based upon this time domain reflectometric technique. So in the normal university or where the cost is very, we cannot afford. So normally people in frequency domain use, and there is called network analyzer, and it also depends upon the what frequency you are using. LCR meter is some frequency megahertz range. X band, most of the university are using the X band and C band to understand the basic sciences in the microorganism. Whereas time domain technique we have just developed and established the SRT University Nanded, and because it is single measurement cover the large frequency band, so whatever the bands we require, and this measurement is rapid and accurate, and it is sample is required. That is the advantage of this time domain reflectometry. And what are the applications where it is used? So if you see that time domain reflectometry total is broadband spectroscopy, but we are using only time domain dielectric spectroscopy, we will find that there are a lot of application in the different field, particularly in the biophysics, proteins. So we can see the protein information by using the TDR, and some people are using amino acid, water. So, but you require different frequencies. So in time domain, we will get the information from up to cell to up to water. So within 1 second, we can measure all this information. So what are the people are interested? People are interested to find out the permittivity. At low frequency, you will get the people are interested. Low frequency is an ionic conductivity. Ionic conductivity, the surface charge, bound water. So as you go on higher frequency, you will find that there are different what? Okay. So we'll get the information about surface charge, bound water, and in biophysics particularly, see that this is the where it is. So in biophysics, in low frequency, you will get the particularly whether it is a protein or any entity, you will get the rotation of that molecules. And if you go higher frequency, the slightly different information will be. If you go again higher frequency, you will find that is free water molecules. So at a time, you will get the information within the time domain reflectometry. That is the main advantage of this. So what is time domain technique? In time domain technique, basically, step generator is required, which produce the fast rise type pulse, and it is transmitted through transmission line. This is the coaxial transmission line, and at the end you can put any sample depending upon your interest, and then sampler circuit is there. It will sample and we can display on the oscilloscope. Right. So transmission line having some specific impedance. So depending upon material used, so impedance will change, and then you analyze in the oscilloscope. So this is our TDR, in which we are using the Tectonics company. This is TDR sampler model, and digital analyzer we are using for sampling purpose, and computer, and this is coaxial transmission line, and this step pulse which is generated from the TDR unit and propagate to transmission line. We can be just, it is a radar type unit, just, and this is oscilloscope. We see that there are different channels depending upon your frequency interest. You can connect this channel, and this is coaxial line. Microwave or step pulse is propagated through the transmission line, and then it will reach to your particular sample. So my work is based on the biomolecules, polymers, and polar liquids, and this is flat-ended coaxial line. Coaxial line means there is a transmission line, and we can detect, and you will get the sampling circuit, and then make the Fourier transform of this pulse. So we will get the information about the complex permittivity after Fourier transform. So this is our sampling scope, and it is a unique facility in India, we can say, available in SRT University from 10 megahertz to 30 gigahertz. We have used this particularly sampling oscilloscope DSA82 Tectonics USA. This is our temperature dependent facility. So we made a local arrangement. It's just freeze arrangement. We can put the sample inside and then maintain the temperature of the sample. This is our laboratory. You can see that this is a local made arrangement, temperature control, because it is a coaxial line. Put inside and then put sample inside and maintain the temperature, whatever temperature. This is the heart of the time domain reflectometer technique. What is this? Is incident pulse generated from the state generator, and then it is round trip delay, open circuit, whatever the cable we are using, and then depending upon the sample of interest, you will find that now it is open, so you will get the addition of incident pulse. So this is step like pulse we will find same as incident pulse, and once if you add some dielectric sample, you will get this type of behavior. If you add conducting sample, you will get this one. From this we can calculate the DC conductivity and all those. This is time dependent, and once you take the, this pulse, we can add and subtract in the computer and programming. So what is the time domain reflectometry? You get the voltage and number of points in the oscilloscope, and then we digitize this point up to 2000. This is a photograph of this picture. So what information we get? Epsilon star omega, it is C velocity of light, D, and P of omega and Q omega is the Fourier transform of these pulses. On that basis we can calculate the this information. What we get? Epsilon star, epsilon prime, and epsilon double prime, which measure the how much energy from the external electric field is stored in the material and how much energy is absorbed by the material, lost in the. So this is the main graph from we'll get from TDR. It's static dielectric constant at 0 frequency, and then it is absorption. So at depending upon what frequency you are interested. Again here loss is 0 starting from here, and then it is maxima, and depending upon sample of interest, depending upon temperature and chemical composition, you will get a different stage. So this is a cold plot, normally in plot. So if once you get this complex permittivity, we can fit this to the theoretical model, and you will get the dielectric constant at low frequency, relaxation time in picosecond, dielectric constant at high frequency, and the omega is a frequency dependent. So it is called as the Harmony-Nigam equation, in which there is, depending upon sample of interest, you will get the alpha and beta parameter that we can discuss later on. So there are different models used in dielectric field, that is Debye model, cold model, and cold division, and another model, 2 Debye model. In particular, this model is useful to biomolecules, and once depending upon what frequency you are, suppose the low frequency we call it the primary frequency, and then we will get the tau1 relaxation. If you are going higher frequency, you will get the tau2. So this is the graph. You will find that particularly lower frequency and another dispersion. If you go higher frequency, you will get the different dispersion. So I will take I will explain only one spectra which is related to the alcohol. What I did here is the methanol is a 1 carbon atom and 1 OH group, then ethanol 2 carbon atom, 1 OH group. So here I have just taken 1 OH group, only carbon atom I think. So what we observe that once you go from 1 carbon atom to up to 3 carbon atoms, so we will find that the epsilon prime value decreases, dielectric constant decreases, and this is the what is called dispersion we find in here. So dielectric constant 33 to up to 170 70 because of the carbon atom if we increase. Whereas the epsilon double prime also we found that shifted to lower frequency. So see that this is a methanol and then ethanol, then propanol like that. So these are the information you will get, and this is the how molecules are relaxed, what time it takes to relax. That information we get from this graph. So this will find that if 54, 162 relaxation time as we go on, number of carbon atom increases. One example I would like to tell you, ethylene glycol is again 2 OH group, and here is also 2 OH group. This system we consider as a 2 OH group. Only position of OH group is changed. So again we will find that this is change observed in the complex permittivity, right? This is called dispersion, and this also we will find that dispersion, loss factor is shifted to lower frequency as you go on the higher what is called carbon atom, or OH, if you change the OH group position. These are the example of polar lipids. It's a very good example because water is very important in life. So that's why we studied this one and published in Physica B. We'll find that the dielectric constant start, and these are the experimental value we reported here. And the theoretical we calculate direct from DY model, and we find that good match. And another example we published in different field. These are the proteins molecules we studied on and compared with the water molecules. These are the DNA molecules, amino acid molecules, and this result, see that these are all polymers, polyvinyl K. There are 60% is a polymer and 40% water molecules is dissolved in it. So this we publish in the international journal. We find this temperature dependent study. These are the polyethylene glycol we published in this one, and this is very interesting observation we observed. This is the graph for the both islands crystalline protein. Normally our eye contain the maximum water, 70% water, and near about 35% of the other organic material in the eye lens. So this we taken as a one example in boat and make a buffer solution, and we found that these are the absorption, dispersion, and these are the absorption. There are 3 peaks we observe. One is beta, alpha, and gamma. So these what information we will get for from this graph, that some medical physics point of view think the whatever the lens, what is the called a transparency or refractive index. So whether it is useful, or the lens is useful for see the vision or not, or to get the solubility of that proteins. Whether this soluble is good, then this is useful protein solution, or this is useful lens. So that's why this graph is very important to understand the lens function. Whether transparency is good or whether refractivity is good. So from that graph we will get and what is the relaxation time also we can calculate from this graph. This paper we published in RSS Advances without review. They accept our this paper, and in the because it's a very interesting, and our aim is to again enhance this facility or enhance this study in future. These are another aqueous sugar we have selected. Aqueous sugar means each are having the same OH group and same carbon atom. Those we have selected on 2, and these are very useful in solar heating purposes. This type of alcohols. This also we publish in Journal of Molecular Liquids, and this also we publish in the 2-sugar alcohol we publish in Journal of Physics and Chemistry of Liquids. This is very important because we publish one water molecules and dioxazole molecules and mixed together in Journal of Physics B. So water molecules and diatom molecules quite easily, because we'll get the information about the structure in terms of hydrogen bonding, and addition of hydrogen bonding, how much hydrogen bonding is modified. So that's why this study is important. So we find that there is a change water molecules, then we add the diatom molecules, we find that there is a modification in the dispersion curve as well as absorption curve. And this is, we say that whether it is how it relates, what are the model is fit, we can get the information. Right? So this we fit in the 2D by model and try to understand this water structure. Again we say that in lower frequency we will find that very interesting result. Water diatom when mixed together, we find that at particular frequency this relaxation time is increased, whereas at low frequency again it decreases. That's why it gives lot of information whether how many molecules are involved in this process, what are the size. That again we will discuss theoretically. Again we have considered ethylene glycol and 1,2-propanediol, and this is a 1,3-propanediol. What is our interest is ethylene glycol or 1,2-propanediol is a polar molecule having some hydrogen bonding and some structure, and you want to change this structure by adding this diatom molecules. So particularly we have selected 2 carbon atoms and 2 OH group here, 3 carbon atoms and 2 OH group and 3 carbon. Only here is change in what is called OH group position. So what is the modification in the hydrogen bonding, that we can study here. So Kurkut correlation factor is hydrogen. Hydrogen bonding means what? Actually hydrogen bonding means you will get the information about the uncertainty finding the bond bonding formation, and molecule, how many molecules involved in that process, how the hydrogen bonding form, right? So Kurkut scientists suggest if you know the dielectric constants and if you know this parameter, we can find out. But G factor determine how much hydrogen bonding is modified, or how much what are the interactions is taken place in because of this one. So that information we get from this Kurkut factor. So what I use, suppose you are adding 2 1-polar molecules and another 2 molecules, another non-polar molecules, we will get G1 equal to 1, then there is no interaction. But there is interaction because we are adding 2 molecules. So that intermolecular interaction we can find out with the help of this one. What is Z11? Z1 is the number of hydrogen bond pair for solute, and cos is the how many dipoles are rotating. Right? Z12 is the number of hydrogen bond pair for solute molecules, and then dipole moment. These are the electric dipole moment and angle between the neighboring dipoles of solute and solid. If you take this consideration, then you will get the information about the nearest neighbor molecules, how the nearest neighbor molecules will be. So what are the assumptions? We assume that hydrogen bond is interaction among the solute molecules and between the solute solid molecules. These are the assumptions we approach for the theoretical point of view. We design this program, and there are no hydrogen between the solid molecules because we cannot take principally 3 interaction. Only we can take over 2 interaction. One either is water or water solvent molecules. There are again we got the number of molecules is 2 or 3, that is our restriction. So what we will get the information? The average number of hydrogen bond. Solute solvent, suppose for example water 1,1. If you take the ethylene glycol. So how we can calculate average hydrogen bonding? Is the N11 is the number of density of hydrogen bonding pair between the solute solvent, and this is the omega is the probability of binding formation. How many bonds are formed, that is the probability we can find out, and this is the number density. When number density we can find easily, but calculating the N1, so probability we can find by using the Boltzmann distribution parameter, and these are the very important factor we can calculate 2 sub-volume hydrogen bonded and non-hydrogen bonded pair. Once you get this information, we can find the fraction of possible hydrogen bond. Once you get the fraction of bond, we can calculate the hydrogen number of hydrogen bonds. See the G1, G2 is the, as you go on, it is the concentration of the solute. So we will find that G1 and G2 decreases at particular position. So this is the x is equal to 0. We will find that near about 2 point value is there. Here we will find that N11 is the number of hydrogen bond, how many bond molecules are involved, is near about 1.9. And it is, as you go on increasing the other solvent, you will find that it is decreases, and it is again it increases. So both will play near about 2 molecules. So one polar molecules, water, oxygen and glycol, interact with the 2 other molecules. That is the work we have. Then this is the we publish in the Journal of Physical Chemistry. So for we have considered 3 carbon atoms system in which different positions are OH group, and we find that G1, G2s are decreases. And we again we consider the 1 propanol, 2 propanol. These are 3 carbon atoms. Only position we change, and we find that at one position we will get the maximum number of hydrogen bonds. So again we compare. These are the 3 carbon atoms with different OH group. These are the 2 carbon atoms and what is called 2 OH group. But different position we find the different different concentration of diazone. We will find the different hydrogen average number of hydrogen bonds. Again we calculate average number of hydrogen bond per unit volume. So we find that this N11 value, this is decreases, but at N12 means mixed with the diazone molecules at particular concentration, this what you call N12 value decreases. Means dipoles are increased. We will find that is the Fourier size is increased. So on that basis we can calculate how many molecules are involved in this particular forming the hydrogen bond. Again we have compared with the 2 OH group and different carbon atoms, we find different positions. So our main object was to calculate the dielectric constant experimentally. These are measured, these solid symbols indicate the TDR measurement, and these are theoretically we calculate with the help of hydrogen bonding approach. So you find that experimental and theoretical values are exactly matched. So means this whatever the hydrogen bonding we calculate and whatever the hydrogen assumption we have assumed, it is exactly matched. And we published this work in Journal of Physical Chemistry. I think it is 2009 it should be. So what parameter we have used? The static dielectric constant, dipole moments, polarizivity, and polarizivity, bonding formation, energy we calculate. Another parameter we have used to understand the hydrogen bonding by excess permittivity. So suppose this is, you know, the mixed dielectric constant and water dielectric constant, and then another non-polar, whatever the modification in the hydrogen bonding because of this molecule. When we add together, so we will get that if it both are same, you will get a straight line. But if it not, then you will find that this type of behavior. So this is the one example I have to show here. So what is the concentration of water, and this is the excess permittivity. You find that this is a negative value in decreases. So this again we tally with our theory. These are the values, and these are the lines shows the theoretically we calculate. So slightly change in the experimental and theoretical values because of some parameter is not fit. So negative values of the excess permittivity indicate the stronger heteronuclear interactions of liquid, and we get the hydrogen bonding information. Most, that is the Brugman factor we determine from this dielectric. Suppose you know the dielectric constant water mixture and dielectric constant water and the volume fraction of the water. So what information these are suggested by Brugman? It is linearly decreases, but in our experimental we find that it is not linearly decreases. It just decreases exponentially. So we modified this equation and we find out the A value. So what is A? A is the assumed as a modified factor, maybe due to structural rearrangement of the solvent, and we determine this using the least square fit method. And another study we perform in the laboratory, that is thermodynamic parameter. So that is very well known, and we plot the log of T versus 1000. So it is also published in Journal of Molecular, particularly for the methoxyethanol water. This also we publish in Journal of Molecular legs as a function of polymerization polyethylene glycol. And this is interesting behavior we observed in the water diazone molecules. See that this is 0.7, particularly the activation energy decreases. Again, this is confirmed with our average number of hydrogen bond, whatever we calculate theoretically. Most of the people are working still in this field, water or core polymers, particularly chemical in 2008, alcohol polymer recently Springer population. And this time domain reflectivity, you will find that there is a lot of application in TDR measurement, human skin detection. It may be used for clinical study of biological sample for cancer detection. We are in the process to tell. Just now I have shown the detection of cataract in the eye lens. This is very interesting work is going on in this field, but it is low frequency. For first time we apply this technique to the eye lens detection. Particularly we have taken the animals as a goat, and we find very most interesting result, and we publish in the advanced researches, advanced sciences. And in the proteins is normally used in the biological or biophysics work on people, and still people are working on the diabetic important target. Some tumors point of view, people are studying these biomolecules. And my conclusion of this talk is number of hydrogen bond between solvent and solvent molecules to diabetic constant. Heterogeneous interaction will get from this hydrogen bonding, and we will get the correlation factor. And the hydrogen bonding between alcohol and OH group, and number of molecules, and still we are in the process, and we are doing. So I would like to thank Department of Science Technology. They produce whatever the facility we have developed in the department in School of Physical Science, SRT University, because of Department of Science Technology. And I would like to especially thank Professor Mehrotra, because he introduced time domain reflective technique in India, and because of that I am here for presenting the time domain reflectivity technique. Thank you very much.
The paper is open for discussions. In case there are one or two quick questions, please stand up and identify yourself and ask it.
For what kind of materials this technique is not very convenient to use?
I will say it is a when high conductivity there, then it is not possible. Only low conductivity is there, it is possible, because the pulse is already short. Once it is short, it is very difficult to make a Fourier transform of that. But normal solid, liquid we can use even.
But in solids it will be
solid it is possible. I have studied, but I have not shown this graph. But it is already people have used this one.
Good. I've got one question that you have shown in one of the graph that as you increase the number of carbon atoms, the psi prime decreases, okay, and the psi double prime psi double prime also decreases.
Right.
So why it is so? What it has to do with the number of the carbon atoms?
Carbon atom, because what is dielectric constant? Dielectric constant dipole moment per. Dipoles are formed there. Depending upon this one, you will get the different dielectric constant.
So this conclusion is universally valid?
Yes, it is universally valid.
You tried for some other?
Yes, so many systems I have studied, but I have shown some few examples here.
So if there are no more questions, we can thank him and for this very interesting presentation.
Thank you.
So next speaker here is Dr. The R&D opportunities in the country, a case study of microwave tubes and communication. Dr. Joshi, he has National Coordinator of Design and Development of a very high-power device known as Gyroton, advisor of CSI network program and high-power microwave tubes, and he has coordinated 4 international collaborative projects with the University of Lancaster, UK, University of Tübingen, Germany, University of Technical Physics, Germany, and Seoul National University, South Korea. These around 16 R&D projects for space, atomic energy and defense has been completed under his guidance. Major research contributions span over a wide variety of topics in electronics, microengineering, microwave tubes, and ultra-high vacuum technology, and he is a member of several societies like IEEE, IET, etc. And he is a co-chairman of core group of state SMT oriented demonstration projects of DST, and presently associated with the Research Advisory Board of and CSM. So this is my great privilege to invite Dr. S. N. Joshi to present his work. Dr. Joshi.
Thank you, Chairman, for introducing me to the audience. Good afternoon to all of you. First of all, I'd like to thank particularly Dr. K. Sharma and Professor Ritu Jain, as well as all the organizing committee for giving me an opportunity to be here and interact with you, particularly the young minds who are present here. The topic, you see the R&D opportunities which are available in the country, vis-a-vis what is microwave, because they belong to my area, microwave tubes, where at all they are used, particularly in the area of communication. In the keynote address, Professor Chakravarti has given an overview of total electromagnetic spectrum, details of that, as well as what are the possible applications in the various frequency band. So I'll have to slightly change, I'll have to skip some of the things in view of the presentations you already had, try to duplicate that. So the R&D is important. Is you know that what the facilities you have today, particularly all of you have your mobile, the communication, all the things have advanced. If you go just 10-15 years back, nothing was there. These things were not available. And what will be there in another decade, it is difficult to realize as at present. But things will definitely change. So the things are changing very fast in the positive direction. So this is mainly due to the inventions made by our scientists globally in centuries back, and based on those inventions now we are converting them to engineering and technology and getting the fruits of those inventions. So I'd like to tell you some of the opportunities which are available in our country, particularly in the area of physics and electronics. Also, I'd like to be excused because I am a very, very bad throat, so kindly excuse me for the same. I'll skip this because this has already been covered. Now coming straightway to what are the facilities which are available of research and development in our country. All CSIR labs, there is Council of Scientific and Industrial Research, I'll go into detail. Department of Atomic Energy, there is DAE laboratories, ISRO laboratories, DRDO laboratories, DEIT, Department of Electronic and Information Technology labs. In part of these organizations, Indian Institute of Science in Bangalore and Tata Institute of Fundamental Research in Mumbai, all IITs, all NITs, central universities, some of the private universities and reputed colleges who are working in addition to the normal academic, they are also giving thrust to the R&D. That's what I see here also, the way the things have been presented for this university. I see a lot of future in the area of R&D in this university also. So several universities are there who have been pursuing R&D. But major is emphasis I like to give on these 4 or 5 who have been the core strength of in different sectors of R&D. Coming to because this, I belong to CSIR, which is Council of Scientific and Industrial Research. It has 37 laboratories all across India, different parts of the country. And in almost all field of science and technology, you will find presence of CSIR is there. Apart from physics and electronics, you talk of any field, you will find presence of CSIR in different fields. So these are the laboratories have been grouped like this. So like physical sciences, these are laboratories. I come from this sector, Central Electronics Research Institute, which is about 250 kilometers from this place, and we have been working on different areas. And just give you glimpses of that. Then, of course, next group is actually the engineering sciences. These are the various laboratories working on engineering disciplines in different sectors. They are the biological sciences. Similarly, we have chemical sciences and information sciences. So, you take any field, you will find presence of the CSIR is there. In addition to, first I'll talk to CSIR only. In addition to carrying out R&D in different disciplines, we have also established an academy through Act of Parliament, which is ACSIR, that is Academy of Scientific and Innovative Research. And we have been carrying out an integrated MTech PhD program. This is the 7th intake which we have been taken. And across all engineering labs of CSIR, as well as physical sciences lab, this program is running. And this actually, in our place also at Siri Pilani, we have been running 3 such programs in different streams. One is on high power microwave tubes, other on semiconductor electronics, and third is electronic systems. So this is by the selection of the candidate after completing their BE BTech examination as per their merit, percentage of marks, as well as their gate score. They are screened for an interview and they are selected. And the number of intake is limited. Per stream, we have an intake about 8 students per stream. That is almost the maximum strength, which we have 8 to 10 at some of the different, but normally 6 to 8 per stream. That's the situation. These are the different, now other than CSIR, these are the ISRO laboratories which have already been covered by Dr. Chakravarti. He has already given you details of their program. These are the laboratories, but he has already given you insight of the ISRO, different laboratories of ISRO, different centers. Of course, he is representing from SEC Ahmedabad, but there are other different centers and their programs. They have already been described by him. I will not go into detail. Now coming to the DRDO laboratories. The DRDO laboratories are about 52 laboratories, again in different disciplines, but their core strength is working for DRDO. That's they have been working in different disciplines, but what sort of field is there? Aiming to the requirement of defense forces. So these are the various laboratories of DRDO. Then Atomic Energy Commission. This is another unit of DRDO, which all you know, the DA. You all are aware of BRC, where there is Bhabha Atomic Research Center in Mumbai. And in addition to that, they have other laboratories. One other famous is the RRCAT Indore, and there is VCC in Kolkata. Like that, different their laboratories are there. In addition to that, they have also a public sector. Sorry. This publicly funded institute, I am not able to see that presentation, but they have also, in addition to the actual R&D organizations, they have also publicly funded organizations like the, say, Tata Institute of Fundamental Research, JFR is there. In addition to that, you must have heard of this Tata Memorial Research Institute in Mumbai, the very prominent organization in the country, prominent hospital in the country for the treatment of cancer. In addition to that, carrying out R&D in different disciplines, they also have this HBNI. We have been providing, like CSIR, they have started only 5-6 years back, but their training school has been running for so many decades now. They take BE BTech for their program, and they train for another 2 years, then they are absorbed in their system. But in addition to that, the training school has started about 4.5 decades back. But as on today, they have various programs in different disciplines, and in addition to this training program, providing PhD degrees also in different disciplines. Now, what type of support is available to other organizations from CSIR, that is Council of Scientific and Industrial Research? We have a group which is known as the Human Resource Development Group, which is headquartered at Delhi. That group is responsible for organizing their JRF, SRF programs, NET program, and that is the responsibility of CSIR. They do it. They have been doing for regularly for quite some time now. In addition to that, they also promote the research from various organizations, maybe government agencies, maybe private agencies, maybe public sector agencies. you create a proposal, but the proposal has to come from an organization, not from an individual. The individual should belong to a particular group, particular center, particular organization, and that type of support is available. The projects are funded under this program, and for that, if this program, if your project is supported by some of the CSIR lab, if it is technically sponsored, then it is easier to get funding from CSIR. But if at all it is not sponsored by any other agency, any other laboratories of CSIR, even then the projects are funded. But the priority goes to those who are directly technically supported by one of the CSIR labs of the organizations. In addition to that, they also, in addition to this, they also grant for if you arrange a symposium, seminar like that, or if you want to participate in a conference either within India or outside, that type of support is available from CSIR. In addition to that, they have also this program, which also now running for the one decade or so, which we call it CPOILS. That is basically for promoting the science stream. So those who complete the 10th, meritorious students of that particular board, of the 10 of that particular board, are selected for this program, and they are given training in one of the labs of that region, and they are also taken care. Their hospital is taken care. Even their parents are given the traveling allowances, etc. So that type of facility is available with CSIR, promoting particularly the science. Similarly, like CSIR, DRDO also support projects which are again from different sectors. But again here also, if they have again the technical sponsorship from some of the DRDO laboratories, then that gets priority. That is the situation. And they have also funding. Two types of funding they have. One, they directly fund, which is from the headquarters, which is known as ER and IPR, Extramural Research and Intellectual Property Rights Office in headquarters in Delhi. They they directly support projects. But in addition to that, their support is also provided by various organizations, because they under